So what is an HR diagram? In its basic sense, an diagram measures luminosity and temperature. But it can tell us a lot more than just luminosity and temperature. So it can tell us the age or the stage of a star. So for main sequence stars, they won't stay on the main sequence forever. They will also age and become giants and supergiants for some of them. And when they're dead, some of them will become white dwarfs and even neutron stars as well, not pictured here, of course. So if you're given the luminosity and temperature of any stellar object, let's say I just give it to you and I say, hey, I'm giving you a stellar object. It has a temperature of 7,000 and it's got a luminosity of 1 solar luminosity. Well, you go to 7,000 surface temperature, 1 solar luminosity matches up with the sun, and you would have it right here. It'd be a main sequence star. So those are 3 things an HR diagram can tell us, but that's not even the end of it as well. It can tell us even more. So one more thing it can tell us is they can tell us the mass of a star, at least for the main sequence stars. Now, if you get an HR diagram like this, and this could also be considered an HR diagram, I mean, it's measuring luminosity and temperature. In this HR diagram, they literally tell you the mass of the stellar objects. Here's our sun with 1 solar mass. Makes sense, it's 1 sun's mass. And as you go up, it goes 1.4, 1.6, 2. As you go higher, you'll notice that the luminosity also increases. So the more mass you have in a main sequence star, the higher the luminosity. The less mass, the lower luminosity. So at least for HR diagrams in the main sequence, more mass, brighter, less mass, dimmer. Now, one more thing it'll tell you is the more mass of the star, the more towards the blue range it will give you for the color of that star. And the less massive, it will trend towards the red range as well. So you can tell the color of a star based on the HR diagram, and we'll go more on that a little bit later in this presentation. Now, some HR diagrams will also tell you the size of a star. Not all of them. Notice that this one right here does not tell you the size. It just tells you the mass and it gives you a dot. That's fine, but some will. Now, for this HR diagram, notice that the smaller circles for the red dwarfs, because red dwarfs are smaller, and for the giants and supergiants, there's larger and even larger circles representing stars that are just bigger in size. You'll also notice the white dwarfs down here are smaller because, well, they're smaller. They're way smaller. In fact, this isn't even to scale because these white dwarfs should be 100 times smaller than the sun, and they're not, because they would just be a tiniest dot that you wouldn't be able to see on this image if they were. So even though it's not to scale, it can give you a general sense of what's larger and what's smaller on this diagram. Now, I do want to bring one thing over here. Notice that the size, as you go up on the HR diagram, the size of the star gets bigger in the main sequence, whereas you go down in the main sequence, they get smaller. So even if you get an HR diagram like this and it only gives you the mass, you can kind of figure out the size as well, because you're like, okay, if my mass is 23 times more massive than the sun, I know that star is going to be bigger than the sun. If my mass is half the mass of the sun, I know it's going to be smaller. Now, that works for the main sequence, but when you get into the giants and supergiants, everything is thrown out, because a giant star can have the same mass as the sun, yet still be twice as luminous, 100 times as luminous. And the reason for that is, even though even though the sun, when it becomes a red giant, will actually be less massive than it is right now, it's more luminous just because it's so much bigger. It's just because it's taking up more volume. It's expanded outwards. So yeah, when it comes to giants and supergiants, mass doesn't tell you everything about them. And of course, white dwarfs aren't even stars anymore, so they're really out of the gate. But when it comes to main sequence, more massive, more luminous, less massive, less luminous. When it comes to giants, it just depends. One more thing to keep in mind. Oh yes, some HR diagrams will also give you the color of their stars. So for example, you'll see Betelgeuse up here is red because, well, it's got that temperature to be red, like 3,200 Kelvin. The sun, yellow, getting close to white because that's what the light our sun mostly puts out in it. White dwarfs, mostly white, some blue, that's fine as well. So some diagrams will give you the color, some will just give you the color within the graph and then they just give you dots. This one also gives you the color. So it just depends. There's hundreds of different HR diagrams out there. Just keep your eye out and know that they all follow the same trends. They always have luminosity increasing upwards and temperature increasing leftwards. I'll go more on that in a second here. So yeah, let's go over some basics for every HR diagram, things that will be the same for every single one. Every HR diagram will either have stars represented by a dot or a circle, because let's be honest, stars don't form in squares. That's not how gravity works. So circles or dots. Vertical axis will always show either luminosity or absolute magnitude. And I have examples of both right now. Let's go ahead and take a look at that. So this one is measured in luminosity. You can see 1 sun luminosity for the sun. And as you go up, each time you go up, it increases by 10. So 10 sun luminosities, 10 times the brightness. 100 sun luminosities, 1,000. 10,000 sun luminosities, 100,000, and 1,000,000. Going down, you divide by 10. So 1/10 solar luminosity, 1/100ths, 1/1000ths, 1/10,000ths. There isn't 1/100,000ths. This one up here had absolute magnitude. Now this one's a little bit more tricky. The smaller or the more negative the absolute magnitude, the brighter it is. So -5 is actually more luminous than a 0, which is more luminous than a +5, which is more luminous than a +10. So just keep that in mind. I won't give you any absolute magnitude on the quiz, so don't have to worry about those too much, but they are out there. Keep that in mind. Yes, I do want to bring up the not even increments right down here at temperature. So temperature goes high temperatures at left and lower temperatures at right. Now, a lot of HR diagrams you will see online, they are not even scale. Look at the difference between 3,000 and 6,000 here. It's about, I don't know, maybe on my screen about 3 centimeters. But over here, it's about 2/3 of the same length, yet it's increasing by 4,000 Kelvin. So a 4,000 Kelvin increase is less than a 3,000 Kelvin increase in distance. Now, why is that? It makes the HR diagram look a little neater, but I would heavily recommend you don't make any graphs in your real life like this. For HR diagrams, it's the norm, but I'm not going to tell you not to. You can if you want. Just be very cautious if you ever decide to do this on HR diagram. The reason they can get away with it is if you look really closely, they have these tick marks between. So each tick mark they have represents 1,000 Kelvin. But I'm going to say avoid that. I would say make yours evenly. Just make sure you have enough room. Just something to keep in mind when you see it. Also, the other thing, as I mentioned earlier, they have highest on the left and lowest on the right, and that's not normal. Most graphs you have lowest on the left, right, 0, and then increasing to the right. Why they did it is probably something they've always done. Don't do it on any other graphs, but for HR diagrams, it's okay. It's okay to have 0 on the right and a high number on the left. Now, for types of stars, let's go into the 3, I guess 4 technically categories of stars. Main sequence. This is where 99.5% of all stars will land, on the main sequence. And there's a couple reasons. One, most stars are red dwarfs. So red dwarfs don't even become giants. So there you go. Most stars will land on the main sequence because most stars are red dwarfs and orange dwarfs. But other than that, for the main sequence, if you take a look back here at this HR diagram, the only things off the main sequence are white dwarfs, which aren't stars, so they don't count, and then giants and supergiants. And for giants and supergiants, well, they're at the end of their life anyway. They're about to die. Our sun is going to spend 10 billion years on the main sequence, and then only 700,000 years 700 million years on the giant phase. So, yeah, it's not going to live that long on a giant. Once things leave the main sequence, they really don't have that much time in the giants, supergiants. They're on their way out. So most stuff is on here, and then if it leaves here, not for long. Let's put it that way. So the nice thing about the main sequence is it contains most stars. And another nice thing about it is things follow a general trend with the main sequence. More mass, more luminous. More mass, it's bigger. More mass, it's going to be higher temperature. More mass, it's going to be more blue. Same thing if you get less. Less mass, lower temperature. Less mass, it's going to be dimmer. Less mass, it's going to be smaller. So the main sequence is nice because everything follows the same trend. You go up, things increase. You go down, things decrease. The only thing that really doesn't is lifespan. As you go up, lifespan decreases. As you go down on the main sequence, lifespan actually increases because things burn through their fuel quicker and fuel is used more conservatively as you go farther down. It is curved, and I'll go more on that in this next slide in 1 second, why it is curved. right here. So the reason the main sequence is curved is because there's a reason, or there's a relationship between temperature and luminosity and radius and luminosity. So for luminosity, temperature affects luminosity. The higher the temperature, the brighter the star is going to be. But it's not just like, okay, you double the temperature, you double the luminosity, make it twice as bright. No, no, no. You double the temperature, you make the luminosity 16 times brighter. So I can't even call that like squared. It's like squared to the squared. So it's a lot. But you double the radius, you don't just double the luminosity, you actually quadruple the radius. So that one is squared. So increase the temperature, goes up by 16 times for a double. You double the radius, you increase this by 4 times. So what happens is, as you get stars with more temperature, they get more luminous even faster. And that's why it's curved upwards as here. As you drop the temperature of stars, they get less luminous even slower. So that's why it's curved down right there. Now I'm going to give you the formula for this on our next live session. So if you have a calculator somewhere, have it ready for Monday, because we're going to be starting to doing our first calculations on Monday. Yay! We'll go more on that next live session. What about giants? So we talked about main sequence. What about giants? Why are they where they are on the HR diagram? So giants, one thing, they tend to be about a half to maybe even a fourth as high as the temperature as their main sequence counterpart. So for our sun right now, it's about 6,000 Kelvin. When it becomes a giant, it'll be about 3,000, maybe 3,200 Kelvin. So it'll be about as half. Its temperature will be about as half as much as it is right now. So you would think, okay, it'll be about 16 times less luminous. But here's the thing. Our sun will get 100 times larger than it is right now. So even though it's going to be 16 times less luminous from its temperature, its radius, it'll be 100 squared. So that's a lot more luminosity from its radius. So actually, it turns out it'll be a lot brighter when it becomes a red giant. And it's true for all the giants. So even though their temperature drops, they can still be brighter. And kind of the same thing, equal and opposite, goes for white dwarfs. So white dwarfs, they appear really dim, even though their temperature is double to sometimes even triple what their main sequence star counterpart is. They're a lot smaller than our sun. So let's actually go take a look at the HR diagram right now. Take a look at giants, and you see over here, giants, they're 10 to the 2. They're about 100 times brighter than the main sequence stars, 100 times more luminous. And the white dwarfs are 10 to the negative 2. They're about 100 times less luminous than main sequence stars on average, if you consider our sun at 1 solar luminosity average. So they're almost like opposites, giants and white dwarfs. Now, it doesn't hold true for supergiants, but yeah, think about that. Equals and opposites almost. Okay, so last thing we're going to cover is stellar classifications. Now, stellar classifications are based mostly on spectral lines that arrive into our telescopes. And those spectral lines can be influenced mainly by the surface temperature of the star. So for now, all I will say is, think of spectral class as what temperature is that star's surface. So for spectral class O, it's 30,000 to 50,000. Basically anything 30,000 plus. B, 11 to 30. A, 7,500 to 11,000. F, 5,900 to 7,500. G, which is where our sun falls, 52 to 59. K, 39 to 50.